Hello everyone, welcome back to my channel. Today I'm going to talk about the natural frequency of 2D truss structure, and I'm going to use the finite element method and the Python code, and I will develop a small program, and then I will show you the result of the natural frequency and then compare the result with the one from SAP2000. And this is the example that we're going to use in this video. So before we start, please don't forget to subscribe and hit the notification button, and if you like this video, please put a thumb up as well. Okay, so I'm going to show you the load which is applied on this node, but for the natural frequency, this is not important because I'm going to use only the mass from the survey of the structure. So there are no additional load for calculation of the natural frequency. And you can show the natural frequency by show the form shape and choose the load case module and apply. And you can see here mode number 1, we have the period T and the natural frequency F, and this is the Python code that I'm going to use. So this is the code that I show you in my old video about the structural analysis of 2D truss and 3D truss as well. So if you haven't watched those videos, please check the link in the description before continue watching this video, so you know how to write this code and can perform the structural analysis of 2D truss. So the truss for the truss we have the Young modulus 10,000, and this is the density of the each member, and this is the unit of the density. And I already import the node coordinates and the bar connectivity as well. And this is the truss. We have the load here, and this is the support, and this is the section of all the member of the truss structure. So we have a class here. So for the first part is the input property of the truss structure. So we have two methods in this class. The first one is the init method, and in this init method, we only want to define the initial value of the truss structure. So we also have the degree of freedom, load support condition, the section, and this is the result that we want to show. So we have force, stress, displacement, and reaction force, and this method is for the structural analysis. So we start with the calculation of the length, and then we form the structural stiffness of the structure. So in order to form the structural stiffness of the structure, we need to define the degree of freedom for each node. So in one node we have 2 degrees of freedom, and this is the stiffness matrix for each member. And you can check in this book It is a good book for the start of finite element method. You can read this book, and you can see here. So this is the transformation matrix. We have the C and S. C is the cosine of the alpha. S stand for the sine of the angle, and we can define it by divide the difference of the coordinate of the each member by the length. So we have two direction, X and Y, and we can form the transformation matrix here. And C here is the value from this line, and A is the transformation vector. And you can use the transformation vector to define the internal force of the truss structure. Now K is the stiffness for each member, and this is the formula, and you can also check in this book. So K here is equal to EA over L, and multiplied to the 4x4 matrix, and this is the value here. So I put the same thing in this Python code, and then we can find the stiffness of each member, and we can form the global stiffness of the structure. And now we can find the force and stress displacement or a reaction as well. Now we'll show you the result of the structural analysis first. So for the first one, I will print the internal force. So you can call the value force here, because we define the value in this method of this class. And next one, I will show you the reaction forces. And I will run this file. So we have the internal force and reaction forces. Now we can compare with the result in SAP2000. So this is the internal force. You can check the first member here. It's equal to 24.99, and you can check this value. And for the last bar here, minus 6.33, and this is the last bar. You can check here the value, and you can also verify the reaction force. As you can see here, and you can check with this one. So everything is okay. Now I will start implement the dynamics parameter in order to find the natural frequency into this Python code. So first I'm going to add another variable. I'll call this f. will be the natural frequency f, and just input only one value here, but it will automatically change after we do the calculation. And next I'm going to add the global mass matrix. So the size will be the same with the size of the global stiffness matrix. And you can check in this book as well. Sorry. So this is the mass matrix for each member of 2D truss structure. So there are two types of mass matrix that you can use. You can use the consistent mass matrix or lam mass matrix. But in SAP 2000, it used the lam matrix. So I'm going to use this one as well. But you can use any one of them. The result is not so much different from each other. So we already have the transformation vector, so we will use this one for the mass matrix as well. But right now I'm going to form the mass matrix for each member first. So as you can see here in this formula, we start from row AL and divided by 2. Rho is the mass of each member. So we need to divide the density of each member by the gravitational acceleration, which is g, and in this case it's equal to 386.09 because I use the imperial unit, and this value here is for the gravitational acceleration in inch per square second. And also I need to transform the pound to kips as well, so I need to multiply this by 0.001, and we need to multiply by section A and L, and then multiply by this matrix and divide it by 2. So this one will be a self section, and length, and divide by 2, and multiply by the mass matrix. I'm going to copy this because the size are the same, but I need to change the value here. Okay, now we got this the mass matrix for each member. We can form the global mass matrix of the structure using the same method for the stiffness matrix as well. I'm going to change this to lam mass matrix. And copy and paste this one, and I change this to M. So as I mentioned, we need to use the transformation matrix as well. So this is the transformation matrix, And next we call this mm, which is the global mass matrix, and everything is the same. Okay, next we need to define the mass matrix at the free degree of freedom. So all you need to do, just use the same method here for the stiffness matrix. So I copy this and paste it here and call this one MFS, and this is MM. Okay, now we got the mass matrix for each free degree of freedom, and now we can find the natural frequency of the 2D truss structure. So we add the information here. Let's say dynamics analysis. So first I need to find find the value here. So you can find the natural frequency by solving this equation. So in order to solve the equation, you can solve for the eigenvalue problem, and then you can find the solution for the omega square, and then you calculate the square root, and you can divide the omega by 2 pi, and then you can get the natural frequency. So first I call this matrix, it's equal to the multiplication of the inverse matrix of the mass matrix with the stiffness matrix. So we got the value inside here, and then we need to solve for the eigen value. So we call this W2 and VR. So W2 is the omega, the square omega, and VR is the eigenvector. But in this video, I'm not going to use the value eigenvector here. So I will not talk in detail why we need the eigenvector. So you can use the numpy command in order to solve for the eigenvalue. And next you can find the value omega by use the command sqrt. It stands for square root of W2. But you need to rearrange the value as well, because the natural frequency we need from the lowest point to the highest point. So we can use the command from numpy as well. So the first value will be the lowest one in this array. So next you can find the natural frequency f by divide W by 2 pi. So now you got the natural frequency. Okay, so everything is complete. I'm going to print the result. We call this natural frequency. and f from this class. Okay, now I will run this. So this is the result. We have 12 value, and you can check the result with the one from SAP2000. So this is the first value, 23.002, and you can check here. So the result is okay, but you can also check for another value as well by showing the analysis result and module information and module periods and frequencies. And this is the result. So there are 12 natural frequency. We can check the last one here, 349, with the last one here, 349. So this is how you can find the natural frequency of 2D truss structure, and you can use this same concept, the same method in the code I show you in this video for any type of 2D truss structure out there, and I hope you can apply to your own project. So this is it for this video. Thank you for watching, and see you guys in my next video. Thank you.